Okay, so due to the cold, we won't be having class today, but I still want to make sure we cover chapter 4 and 5 so that we can not miss any days in the future. So we're going to start by covering chapter 4, which is about using libraries. We've already talked a lot about simple pick, which is a very simple piece of code that uses just special function registers to make LEDs blink back and forth. One thing that this piece of code is missing is the ability to talk to the computer, sending text back and forth the same way that we debugged our code using just plain old GCC. And so talking pick is a method of doing that. But of course, sending text back and forth is complicated and uses some special function registers we haven't discussed yet. We would like to use these straight off the bat. So we've written code that uses a library to do that. And once we've kind of caught up, we'll go back and look at those libraries to talk specifically about those special function registers. But for now, let's just see how do we use a library and include it in our code. So here we're going to include nu32.h, which is an H file and a C file that contain the functions that will make our code run faster and be able to print and receive text from the computer. So here's what talking pick looks like. We can immediately see it's a lot shorter because we're taking advantage of using functions instead of writing out all the code. We call nu32 startup, which is a function that's going to make our code run faster. And then we have a read and a write function. So the read function will receive characters from the computer, and the write will send characters to the computer. So let's see how this works. We included the H file, so we can go take a look at the H file. It, of course, starts with our include guard. It includes xc.h, so that's where we're going to get our special function register names from. It makes some pound define so that we don't have to remember that our LEDs are on F0 and F1. Now we can just refer to them as LED1 and LED2. It also gives us a name for our user button, and the speed of our system clock, which we might need for calculations in the future. And then because it's H file, it defines some functions. We have startup, read, and write. And if we want to see what the contents of those are, we have to look at the C file. So nu32.c contains a lot of stuff. So the first couple things it contains are pound pragma config definitions. So we talked about the special function registers, the device configuration registers. These are the ones that are only set by the programmer, special values that tell the pick how fast to run. So these are defined here. They're of course not used here because they're set up by the bootloader, but they're here for your reference. Then we get to the content of the functions themselves. So here's nu32 startup, and this is a function that we're going to call in every piece of code we write from now on as one of the first pieces of initialization code. And we'll cover all the functions that are in here, so you don't have to know exactly what this means yet, but here's a function that makes sure that we run as fast as we can. Here's some special function registers that set up pins. Here's the initialization of our LEDs, so here's making the LEDs outputs, here's turning one off and one on. And then here's the initializations for the UART, which is the communication between the computer and the PIC32. Then we have a read function and a write function. The write function is a little easier, so we'll start there. We're going to send a pointer to an array. We're going to have made that array with the sprintf function. The last character in the array will be a 0, so loop through every character. As long as it's not 0, send it to the computer. And then once you hit 0, you're done. So that's how we send stuff to the computer. And then if we're reading text from the computer, we're using the read function, so we're going to store things into a pointer, and we have to remember how many things we had left in that character array so we don't accidentally overrun things. So this is just a little algorithm that reads one character at a time from the computer, stores it until we get a /n or /r. So this is some simple code that just demonstrates using the nu32 library, reading and writing, and starting up. Occasionally, though, we won't have access to a computer. So maybe you've programmed your PIC and you don't want to be plugged into a computer to send things back and forth. We might use something like a character display. So this is a character display that you'll receive. Each slot here can display a letter or a number. So it's not like a cell phone screen where you can set any pixel to any color. It's really just the pixel is on or off, and you specifically say, I want an H here, and then it knows what an H is and draws it for you. So you get 16 letters in a row, and you get 2 rows. So these special character displays, of course, are controlled by pins. And you'll be building this circuit between the LCD and the ME32. Takes several pin connections. And of course, that means there'll be a library for initializing those pins and being able to talk to this device, which needs special commands in order to do things. So when we look at a library that talks to this display, here's what some code will look like. So we're going to include ME32.h because that's where we're going to get all of our initializations for just the PIC itself. And then here's our library for LCD functions. And here's what code looks like from now on. So we'll define variables. We'll call ME32 startup to make sure the PIC is running as fast as possible. We'll call our library function that initializes the pins, in this case for the LCD. And then this particular piece of code asks the user to type in some characters. It then clears the LCD screen, moves to cursor position 0, 0, writes some stuff, moves the cursor again, writes some more stuff, and then asks the user again. So it's just demonstrating how the LCD works. So when you get your LCD in your PIC, you'll run this code just to verify that you built the circuit correctly. And then later on, we'll continue using the LCD for debugging purposes. So chapter 4 is pretty quick. What we really want to talk about is chapter 5. Chapter 5 we call time and space. So this is specifically getting down into the nitty-gritty of the PIC that says when we start to compile code, how fast is that code going to run? And maybe if it's a lot of code, how do we know we're not going to run out of memory? So the chapter 5 sample code has a specific piece called timing.c that we'll be investigating. Timing.c works a lot like simple PIC. It's just going to call a delay function and then call a function called toggle light, which just inverts one of the LED pins. But instead of using just straight special function registers, we're using ME32 startup to initialize the PIC as fast as possible. Then we're calling a delay function, and then we're calling a toggle light function. So the delay function is just a for loop. For loop is just going to iterate delay times, in this case 50 million. And then every time that ends, it's going to go to toggle light. And then we have several methods now of inverting a pin to turn an LED on and off. So the easiest way is to say that the pin is on F1. So if we grab the value of lat F1 and make it equal to not itself, that's the same way as inverting it. So we're basically saying if it's a 0, not 0 is 1, so now it's a 1, so now it's on. Then we're going to delay. Then not 1 is 0, so then it turns back on again, and it just oscillates back and forth. Of course, we have another way of using the lat finv special function register, which directly manipulates that one bit and flips it. It's a little harder to remember, and we have to remember what hex 2 means and stuff like that. So this is a little easier to read and figure out. And what's the advantage of doing this over this? Well, it's easier to read, but maybe this one will work faster. How do we know it's going to work faster? Our make file contains some extra things that we didn't type in when we were compiling simple PIC with just GCC. It had something called this cflags variable, and the cflags variable has this -g -o1. This is capital O, not a 0. 0 usually shows up with a slash in it like that. And the O1 is what we care about here. O1 means optimization level 1. So whenever you use the make file, by default, the XC32 GCC compiler is going to be using optimization level 1, which says after the code is compiled, try to reduce the code size and make it run a little faster. If we were to delete that line, use optimization level 0, which is just flat out GCC, no attempt at making things faster or smaller. And then if you were to pay Microchip for better versions of the compiler, there are other levels which would try to reduce the code size, which is important if the code is very long and you're running out of flash memory. Or it would optimize for speed, in which case it might take loops, like a for loop, and it might not leave it in for loop configuration. It might actually just turn the for loop into hard-coded, 100 times do this one thing. That would take up more speed, that would take up more memory in your flash, but it might run faster because what we'll see is it won't have to jump around. The code will just be linear. And we saw from caching that when you don't hit non-linearities in your code, caching runs really fast. So how do we know what's going on here? When you run make on a folder that contains your C code, it's going to make some other files. One is the dis file, the .dis. That stands for disassembly. This is a very interesting file. This is a kind of a record of what the compiler is doing to your C code as it's going through the compile process. So eventually it's going to take your C code, turn it into assembly code, and then assemble that into object code. And the object code is the raw instruction that we're going to see. And this file is very, very big, so it helps to just find things. And so what we're kind of interested in, like, where is main? So if we do a find for main, it brings us to like this weird interlaced piece of code that is like, here's our C code. And here's what happened to that C code. It got turned into these lines. And so the literal like final executable says at this memory address 9D0020A0 put this value. We don't know what that value is. It's some kind of binary thing, but the CPU would understand. The CPU would understand that that means run this assembly command, and here are the inputs to that command. Now, our CPU is a ME333, and the ME333 has something like 128 different possible assembly commands, and we don't want to even look those up. We don't care what they are. The important ones would be that anything starts with a J means jump, so it means jump to some location. And each one of these lines takes one system clock cycle to run. So this particular line takes 1/80 millionth of a second, and then this next line takes 1/80 millionth of a second. So if we're looking at our code and we want to know how long it takes to run, we're just going to count how many lines there are in assembly. So how does this code work? When it first turns on, it must do these two lines, which basically turn on the PIC and get like RAM going. And then the next line in C says, call this function ME333 startup. So what does that do? It says jump to some other location in memory. So we're currently at this location in memory. We're going to jump to this location in memory. And probably what happens is when this function is done, we're going to jump back to the same spot, and then we're going to move on. So let's pretend we did that. We jumped to ME333 startup. We ran the code that was there. Now we've jumped back. No op here means take one cycle to just do nothing. And then we're going to continue. So now we jump into our while loop. The while loop has a delay function. The delay function, of course, is a function. So we're going to jump to this location. That's going to jump us back when it's done. Then it's going to call toggle light. It's going to jump to this location. It's going to do that. And then it's just going to come back and forth. And that's what the for loop will do. So if we want to know exactly how long our delay function works, we would jump to this location. So we could either find that, or we could try to find delay. Our code's pretty linear, so it's basically just down here. So here's the delay function. It has to do a for loop, so this must be the assembly version of how to do a for loop. Okay, after it runs delay, it's going to call toggle light. And here's what we're really interested in. So the toggle light function takes this line of C, which says whatever the F1 bit is, let's invert it so that we're flipping the LED. And so that one line of C got turned into 1, 2, 3, 4, 5, 6, 7, 8, 9 lines of assembly. So it would take 1/8 millionth of a second, because that's almost 10 cycles at 80 megahertz, to flip that one LED. So what you can do is you can go into this makefile. You can delete this, or you can replace it with 0, and then run it again, and you'll see a new disassembly file created. And rather than the optimization level creating this line of code, you'll see a different amount of code because it will not have optimized anything. And it might take longer. It might take more lines of code to do this line. And then you can comment this line out and see and uncomment this one. Run it again, see how many lines of assembly this would take, and probably it's going to be faster. So in the homework, you'll be doing that for a bunch of different methods, including different mathematical calculations, and you'll be able to see, when you take two numbers and add them, how long will that take in code? The answer is find the function where it happens, count how many lines of assembly there are, and each one of those lines takes 1/80 millionth of a second. The other thing we're probably interested in is how big is the program going to be in memory? Like, how many bytes did it take up? So another file is created when we run our makefile, and that's called the map file. So the map file contains kind of a list of like every part of the compiler that was run, and every O file that was linked, and every possible like piece of memory that was touched. It's very long. It's kind of hard to find stuff in it. So what we really care about is like, where's main? How much memory did main take? So the same thing, we're going to find main. And so if you remember the memory map, we've got these sections of memory kseg, kseg 0, kseg 1. Kseg 0 is where our flash is, so this is where the program lives. The .text of kseg 0, it has this report that says how much memory did our program take. Pretty short program, so it took 452 bytes of memory to store our program. It also says something like kseg 1 usage. kseg 1 data memory usage is RAM. Now we didn't declare any variables, so it doesn't have anything in there. And because it didn't use anything, that means that the remaining RAM is stored in something called the stack. So the stack is like how much RAM is there available for functions to use. And that's all of it. And interesting thing here is that we usually say that our PIC has 128K of RAM. Their definition of K is different than 1,000. So here's the actual number of bytes of RAM the PIC has, 131,000. So other things that are interesting in the map file would be we have these functions main and delay and toggle LED. Where are they? So if we look for toggle, here are the addresses of all our functions. So main is at this address, and then delay is at this address, and then toggle was at this address. And so from the disassembly, we could have seen that as well. The toggle light function was at E8. And the map also says we're at E8. So the map file and the disassembly file kind of give us similar amounts of information. The map file is more about how much memory was used. The disassembly file is more about how fast will your code run. So take a read through chapters 4 and 5. 4 is more about how do you use library files. Chapter 5 is more about how fast is your code going to run and how long will it take to run and how much memory does it use. And we'll address more of this in class.